Okay, so today we're going to be going through the loss function and its derivative. But first I do need to make a couple of changes. One fix and then a couple other changes. Okay, so right here in the layer dense backwards, here for layer bias, for going through the bias, I actually want to make a change on that. I was initially thinking, and had done this somewhere else, going through the derivative of the biases rows and columns or d-values. I was thinking d-biases and d-values would have the same shape, but that is not true. So they both have the same shape in the number of input dimensions, but the biases, which would be the same shape as d-biases, there's only one set. There's only one with, so it's a 1 by input dimension, whereas d-values will be the number of samples by the input dimension. So we're going to switch this to d-values. So we go d-values.rows is the number of samples, and d-values.columns is the number of inputs. And then this needs to switch to 0, j, I believe. Yeah, okay, so that fixes that. And then just in prepping for this video, I fully built out the thing and was looking at some different stuff I need to tune. So right here, which these numbers may need to be tuned differently for different types of architectures, or like different. I think usually these numbers here will be fine because usually you'd be working with bigger data sets, but which I used this for the MNIST data set when I had built that a while ago. But right now we're going to change this to -1 to +1, and we're going to change the biases to initialize from -0.1 to 0.1. And that should make this work better. I'll put a 0 there. Okay, so save that. And then we will come down here, make a class for the loss function we have here. We'll be using here, which will be binary cross entropy. Loss. So for the constructor, I'll have it take number of samples and number of columns, which will be the number of outputs or number of classes if it's if you view it in a cross entropy. But this it should just be 1. And this backwards function, it says it's taking in derivative values, but that's kind of just to keep it in line with everything else. Sorry. Does that fix that? Oh, that's... There we go. Okay. So what I was saying is this backward function, it says it's taking in d values, but that's just so we keep everything the same. The backward values are always taking in d values, but but for this one, d values will actually be the output of the sigmoid function, which that will also be the y predictions as well. And the forward here will just make the output the losses, which are these sample losses that we'll have. These y predictions clipped. Show you more here in a moment in the, I think it's the forward pass. Yeah, in the forward pass. But basically we're going to have to contain the y prediction values, these sigmoid outputs. We're going to have to contain those to certain bounds, because if they go too close to 0 or too close to 1, they kind of blow up the log function that's within our forward and backward passes. So we have the y pred clipped. And we'll do the same with the d values. Have to clip it, which just means contain it within a certain amount. Okay, then I'm just gonna copy and paste this. Allocating the memory. Allocate memory for our different things up here. Y pred clipped, sample losses, clip d values and d inputs. And these are dimensions of them all. These two will be the same dimensions. They will be the same as the output of the sigmoid, and actually all of them will be the same there. And this forward function, you actually is not required for the training. Like I said, it'll just output the sample losses, or basically calculate the loss of the prediction, like how far off it is, a value for that. Otherwise, it's not really needed. Guess I probably need to put that in a for loop. So yeah, we'll be using this clamp function. Which all it does is take in each value and takes in a float. Or I'm sure there's a double version as well. But takes in your value. So that's why we're looping through this whole thing. Each value takes it in, and it will make sure it is between certain values. So if it's ever below this or above this, so like if it was 4 9s here, it would reduce it down to 3 9s. That's so it doesn't get too close to 0 or 1, like I said, and that'll be for this next part here. Let's see, let's move to at true. And this is why right here, using the log function. It goes crazy if you have a number too close to 0 or 1. This is a long equation. And I think I used Grok to find it. The explanation. Yeah, I'll find that real quick. Maybe I use Gemini. Sorry, you don't get to see what my searches are. Okay, we'll come back to that. So we got this 1 minus, what do we got? So y true, y pred, plus 1 minus. Yeah, I definitely don't memorize these formulas. Okay, so there's that. And if that's confusing and like too much all at once, it might just be easier to make it yourself through this breakdown here. So yeah, just go or use Gemini to look up binary cross entropy loss. So here's the formula for it right here. And the loss is negative of this whole value. Your y values, your y true values, times log p, which is log of the outputs of the sigmoid function. So y times the log of the outputs of the sigmoid, which is your inputs to this, which we end up doing as the y pred clipped. So y predictions, and then we clipped it to make y pred clipped, log of that, plus 1 minus the y value, the y true, times the log of 1 minus p, which is 1 minus the output of the sigmoid. So that's what we just coded right there. So we did minus 1 times y true times the log of the predicted value, the clipped predicted values. And then the other half is y minus, or 1 minus y true times the log of 1 minus the y predicted values, which is the sigmoid output. And what this does, it actually evaluates to only one of these two, this one or this one, because either it's y true, it equals 1, and you do this, or if y true is 0, then 1 minus 0 will be 1. So either this area over here is 1 from this y true, so y true being 1 would make this 1 times this value, or if y true is 0, then 1 minus 0 is 1 times this value. If y true is 0, then this is 0, and that's nothing, and 1 minus 0 is something, is 1. But if y true is 1, 1 minus 1 is 0, so all of that's nothing, and this is 1 times this value. So yeah, that's the forward pass we'll just go straight into the backward pass. I'll take D values and Y true. So like I said earlier, the forward pass isn't really necessary for training, but the backward pass is. It's the first thing in the chain of going backward and finding all the derivatives. And once again, we're clipping the values. It's only using one for loop because there's only going to be one output per sample. Then we're calculating the inputs off of that. Let me go ahead and show the formula for this one first. Okay, so this was for the forward of the loss, and then derivative down here. The derivative is negative, again, we'll do y times the log of the output plus, let's see. Oh, no, just kidding. So that's the formula we just had. And then the derivative of that formula here is just the output of the sigmoid minus y divided by the output of the sigmoid times 1 minus the output. So the probability that so the sigmoid output's a probability between 0 and 1. So that probability minus the true value over the probability times 1 minus it itself. So that's pretty simple. Okay, so with that, so p minus y over p times 1 minus p. So clipped d values, which is the output, minus y, which will be y true, and that will be divided by p times 1 minus p, which will be the clipped values again, times, we'll just separate those out. This will be 1 minus 1 minus put comma I comma 0. Let me double check that. Cool. And then just 2. Oops. There. That fixes that. And then we're going to normalize it by the number of rows. Yeah, so there's that. Now we can plug that all in to our main function here. Let's see, so we got that. I'm actually gonna add an extra layer here. Oh, we'll try it without and then see if we need to add an extra. So there's the output. We can do a loss. Oh, I guess we need to make the loss function first, or do the constructor. Binary cross entropy loss, we'll call it loss. Num samples by we'll just put a int num outputs equals 1. Num outputs and then here we will do loss dot forward of the sig output, and that will get our let's see. Oh yeah, we do need the y true as well, which is just y. So this will give us a loss number, but then loss dot backward will actually be useful for calculating gradients. So rather than this having the output, this is actually going to take loss dot d inputs. I'm going to comment these out. Save and let's set forward. Let's also see what we get for the losses. we will print the loss dot sample losses. Save and run. So let's see here. Okay, yeah, so we do need to change the sigmoid to num outputs. That'll make more sense. So these are all probabilities, and these are losses for those probabilities. Now we can, next part will be, we need to adjust the weights, to use these gradients to adjust weights. So I'm going to make a new class. Let's see. That can wait till the next video.